Good afternoon, everyone. We're going to get started here in a couple of minutes. Just want to make sure that all attendees can jump in before we kick this off. So stand by and we will begin shortly. Thank you. All right, well, it's 2:00 p.m. here on the East Coast. We're going to go ahead and kick this off. Good morning, good afternoon, and good evening, everyone, and thank you all for being here today. My name is Charlie Collius, and I am the Product Marketing Manager for the Equipment Group here at AFL. And today we have a very informative Splicer webinar for you titled Unlocking the Secrets of Mass Fusion Splicing. Craig Henderson is he's a Senior Applications Engineer at AFL, and he will go over some helpful tips, real-world splicing challenges, along with best practices and proper use of splicing accessories. Craig will go over all of these through live demos, so get ready. It's going to be a great 45 minutes to an hour. So if you have any questions at any time during this presentation, just add them right into the question box on your screen, and we'll answer them at the end of the presentation. And today's webinar is being recorded, and a link with where to view the recording will be sent out in the next couple of days. So with that, I want to introduce Megha Garalapati and Craig Henderson to start today's presentation. Craig, go ahead and take it away whenever you're ready.
Thank you, Charlie. Appreciate it. We're going to start this session. I wanted to introduce my cohort in crime. Sitting beside me is Megha Garalapati. Megha is a product line manager for AFL Fusion Splicer Group, and he's here to assist and help me manipulate these cameras that we'll be looking at. I wanted to kind of briefly explain the setup and what we'll be looking at today. We have a live video feed, so I'm able to show you various camera angles, and we're going to touch base on what those camera angles are. We'll first start off with the overhead of the Fusion Splicer itself. As you see, this is a 90R Mass Fusion Splicer. It is Fujikura's latest and greatest Mass Fusion machine. And with that, we're going to be showing a number of accessories today. This is our second view, is the accessory view. As you look at this, this is an overhead shot of the various accessories that may come into play today. The hot jacket stripper, the CT50 cleaver, and the ribbonizing tool, along with the splice protector sleeves, as you see here. We also have some cleaning supplies on the side that we'll be talking about quite a bit today. And then we'll move over to the monitor of the Fusion Splicer itself, which we can turn on the splicer now, and I can boot the system up, and you will actually see the splicer boot up, become operational. At this time, it'll start Bluetooth communication with the accessories, which would be the hot jacket stripper and the CT50 cleaver. Over on the far right-hand side, or excuse me, the left-hand side, I have a microscope assembly set up, and this is just a quick view to show you an overhead view. Since we're looking at small parts, fiber and fiber holders, I wanted to show you this view, kind of show you that we've got a cell phone feed coming through a 30x microscope with white light blaring down on top of this fiber. So if you look at this fiber image, this is actually the fiber holder, and I have a linear bearing that I'm running over the top of the fiber holder. And you can see this is a FH70-12 with a traditional ribbon in that structure. So we'll be able to look at these various assembly types as far as ribbon that we would be dealing with, and rollable fiber, a rollable ribbon, along with your standard loose tube fiber that we construct into a ribbon format. So we'll first start out by having some conversations regarding the getting prepared for this. As we get prepared for the splice, a couple of things we want to know about the structure itself. So if I hold this material in front of you, you can actually see that this is a ribbon cable. And within that, you're going to have an ITU classification of glass. This may be a single mode fiber, a G.652. This may be bend insensitive fiber, a G.657, either an A2 or a B3, or it could be multi-mode fiber. So first thing we want to do is identify the type of glass structure internally into this ribbon structure. We'll move into the fiber ribbon structure. And today, and this is kind of, you know, the recipe of giving you what I call best case scenarios with using the proper fiber holders and the various mechanisms that we can bring to the party, so to speak, for as accessories. What we want to do is identify the fiber type on the A side and the fiber type on the B side. In this particular case, this is a match clad single mode fiber. This is your traditional Corning ribbon structure, which is a fixed matrix. And if a scale of 1 to 10, this is probably the easiest to splice in the industry today. That being said, we would use our traditional fiber holders, our normal parameter settings for this splicer. Now, we'll go back to an overhead view of the, excuse me, a secondary shot of the first thing we want to get into when we do machine calibration. I won't cover this too much, but anytime that you touch a fusion splicer, you want to go to your maintenance menu, identify your diagnostic test or your arc calibration test. It's recommended a minimum of once a day to do an arc calibration, preferably first thing in the morning when you start your operation with your equipment. But as we move forward, we're going to get into our standard cleaning processes as well. So I'm going to take another view, which would be a overhead view of the a little drawing that I produced, and show that to you. Very simple drawing that I want to bring to light the main function of any fusion splicer is to align that core for maximum core alignment. With an active profile alignment system, such as a 90S active fusion machine, the V groove would move. But whether it be a fixed V groove, an active profile alignment system, or a cladding alignment system, all the Fujikura product line would hold the fiber the same way. You have a V groove, and of course with mass fusion, we would have 12 V grooves and even up to 16 V grooves. But it would hold each individual fiber in this position. You had the sidewalls of the V groove itself, and then the little V groove chip that would come over the top of it. If I do an overhead view of the splicer body, I'll point these out to you right quick. Can you drill down to the top of the machine for me, Mega? And I will point out the V grooves. Here again, these are 12 individual V grooves. This is a fixed V groove system. And if I open the wind protector and slightly bend it forward, I will slide the splicer up a little bit and actually show you the V groove chip clamps. This is the mechanism that comes over top of the V grooves and will locate that fiber by that 3-point alignment that we discussed earlier. A little bit about mass fusion splicing. When we get into mass fusion splicing, change the view over to the, what do we call this, a presentation mode? The presentation screen? Yeah. So the fiber geometry, when we're dealing with mass fusion splicing, what we really want to do is ensure that we're dealing with today's quality glass. And when mass fusion was first introduced, a lot of mechanisms at play, but until 1990, all fusion splicing was done with an active profile alignment system. When the mass fusion systems were introduced, the fiber manufacturers quickly realized that we had some issues with core cladding concentricity, where honestly the core was not in the center of the cladding. Being a fixed V-groove system, it's relying on maximum cladding alignment. If you get great cladding alignment and you have quality core cladding concentricity, you in fact will get a low loss splice. They have improved this vastly over the last 25 or 30 years, and today it's not much of a problem. So the majority of splices, as you see out there, fiber produced can be done with a mass fusion machine. I will say that with a little bit of a caveat. We're talking about, of course, the industry leaders in fiber technology today. Every now and then you'll get a produce of glass that would produce core cladding concentricity issues, and in turn you would have to splice that with a mass fusion splicer. Flip the page over, look at another issue with geometry characteristics. Simply put, if you do not have a 125 micron cladded fiber, say it's a smaller diameter, 124 microns, you'll notice that the center line of the fiber opposed to the 125 is 124. The core would actually drop below that center line. This would in turn cause axial misalignments. The splice, during the splice, it will last approximately 10 seconds. You will get a viscous self-centering of those fibers. Unfortunately, if you have to move it that far, you will get a lot of core deformity, core smear, and result in a higher loss of that splice due to that fact. So that's some of the material we'd have to cover. I'm going to go and start showing some different variations of fiber. If we can do an overhead of the accessories.
Sure.
Want to talk to you a little bit about some of the fiber constructions that we have. If you can drill down, please. The magnification. So here's a good example. This is the fiber that you see in front of you is, again, the industry that has been in place for a long time. This is traditional fixed matrix ribbon. As you can see, the fiber is laid out with an encapsulated matrix material. You go to some of the fibers that are produced today, and I love this product. This is actually called spiderweb ribbon. If I take this fiber and spread it apart, you can see that it has interlocking bonds, but it will allow this ribbon to be collapsed. So it will allow you to, the beautiful thing about spiderweb ribbon technology, it is what I would consider a cable that can be constructed into loose tube packaging, and you lose loose tube fiber management inside of closures, but it will allow you to mass fusion splice that. So we're going to be working with some of this material and give you the best practices as we move forward. I will also talk a little bit about some of the other fiber holders that we have in the industry, and moving back over to the overhead. Not only do you have your traditional 250 micron pitch fiber, so the old Corning fiber, that would be your encapsulated conventional 250 micron ribbon. You'll notice here that from core center to core center is going to be approximately 250 microns, because the coating edges with a 250 micron coated fiber are in physical contact with each other. And that would relate to when you remove this conventional ribbon matrix, the primary coating, the pitch spacing of that fiber from core center to core center will be 250 microns. Thus, it would align with the V groove inside your mass fusion splicer. This is your conventional ribbon. Ribbonized fiber, as you see on the second image, is a fiber that is loose tube fiber. It has been placed into a ribbonizing tool, and a glue adhesive has been applied to that fiber and allowed to cure. This will work very much like your conventional 250 micron ribbon. The only difference is the primary coating itself has a tendency to have a better bond. It will adhere to the fiber a little bit more. So the characteristics of stripping this with your ribbonizing tool will vastly change. Your heating profile in your ribbonizing tool will change. Here is the spiderweb ribbon with coated fiber. When I say spiderweb ribbon, this is actually a Fujikura trademark, and it has to do everything with this bonding and these tap connections between the fibers. You'll notice here that it resides below the apex of the fibers. And as a result, when you go to strip this, it handles very similarly to a ribbonized cable or your conventional 250 micron ribbon. There are other suppliers out there of bonded, what we call rollable ribbon. You have to be somewhat cautious with that in the industry because the bonding itself can reside over the top of the coating, and that will interplay with your fiber holders. And we'll talk about this a little bit later into the presentation. But bottom line, these are all 250 micron pitch fibers. That being said, we're getting into the latest and greatest in ribbon technology and coating diameters, and the traditional fiber coatings in the industry was 250 micron. Now that is changed to 200 micron coated fiber and even 200 micron ribbon. We have a 200 micron spiderweb ribbon available, and also a lot of our competitors have the same thing. But as a result of this, we are dealing with a 200 micron pitch from core center to core center. So this allows us to actually interchange our V grooves and replace the 250 micron pitch V grooves to the 200 micron V grooves. That gives us what I call an ease of operation best case scenario when we do, we're able to change our fiber holders and our V groove assemblies, ease of splice. Of course, then we get into the other ramification of this when you're splicing a 200 micron to the legacy 250 micron fiber. When we go down this path, we cannot reduce this 250 micron pitch. We can't convert that to 200 microns. So our only option is to take this 200 micron fiber and actually spread these fibers apart to create a pitch conversion where we are moving that 200 microns to 250, and that's kind of illustrated on the bottom of the page with this pitch spacing as you see here. Talk a little bit about fiber holders and various fiber holders available in the industry. This is just a small sample. This is AFL Fujikura's offering of fiber holders in the 250, 200 micron range for 12 fiber. We have actually moved to producing a V groove for 16 fiber 200 micron pitch spacing. So there's a lot of options down here, and that's where you have to do your homework on the front end when I talk about getting prepared, fiber ribbon structure. All this comes into play, ensuring that we have the correct setup for what we're working with. Now, I'll flip over the page for a fiber holder that we have produced here, just to give you an idea of what we're talking about. The illustration that you see on the top is a ribbon that has been separated into 4 fiber segments, 3 4 fiber segments. So we would use a fiber holder. It's called the R200 3x4 fiber holder. The whole purpose of this is to make sure that we're able to manage those ribbons as they exit this fiber holder to fall in the proper V groove space designated with a 200 micron or 250 micron pitch. In this case, we got a 200 micron traditional fixed ribbon that we're having to migrate to a 250 micron pitch and do a pitch conversion with that. So if you look at this fiber holder, you'll notice that it's got three ridges, and this is your separation point to allow us to push that fiber into the proper V groove. A little bit about V groove exchanges. As you can see, a simple replacement of V grooves, it would require a small tool to remove a bolt, actually 2 bolts. You would disconnect the V groove with the electrodes attached to that V groove assembly. A simple switch out of the V grooves in less than a couple of minutes. Then we get into mismatched ribbon. So the equation here, and the way I look at this, if you're doing a 200 micron splicing and you've got A side 200 micron, B side 200 micron, the logical choice is to buy the 200 micron V groove, the 200 micron fiber holders from the standard of efficiency and time as we negotiate and make these splices. Now we're going to move over and start looking at different types of fiber and constructions. Change the image to the camera here. So this is a 200 micron, 250 micron traditional ribbon. As I mentioned earlier, this is the F870-12 fiber holder. And as you can see, there's no separation. I'm actually moving the end of this fiber. And by the way, I wanted to point out something right quick. You see these 2 marks? This correlates to the hot jacket stripper. If I can pan over and show the hot jacket stripper right quick and zoom down. So I'm going to take that fiber holder I just removed, and I wanted to point out something on the fiber holder. As I load this ribbon into the fiber holder, the blue dots closest is this point here. If you look at your hot jacket stripper, you'll see this little triangle heater insignia. This represents the shortest possible length of the ribbon as you attempt to strip that material off. By the way, this length here for minimum directly correlates to the apex of the roller on your CT50 cleaver. So if I'm showing you this CT50 cleaver and I put that fiber holder in here, that mark on your hot jacket stripper would be at this point. One of the things that you want to ensure is your shortest fiber that you're attempting to strip goes over this apex. This will allow your fiber collection system in your cleaver to grab that fiber shard and dispose of that fiber shard into your wastebasket. And that's, again, the longer blue line represents the far end of travel inside your hot jacket stripper, this very far end of travel. So if you cleft this in, you would not be able to remove the material from your hot jacket stripper. So this first show, or the marks on your pad, and I apologize for the color of this. It's a little cleaning white that we use, and I try to use a white background to give us a little bit of contrast so you can see it well. But again, this mark represents the shortest possible distance and longest possible distance. Now, this is the F870 12 fiber holder with traditional ribbon. I'm going to look at another supplier's material. This is 200 micron, and what we have installed is the F870-12-200. You'll notice that the width, even though it's 12 fibers, the width is a lot. The standard width is about 3 millimeters. This particular width is about 2.5, excuse me, somewhere around 2.8, I'm sorry. And as I separate this, you can see this ribbon and its tack pattern associated with this particular ribbon. But as it exits the fiber holder, you'll notice here that the pitch spacing should be in that 250 micron range. That's sample number 1. I'll move over to a traditional Corning flat ribbon, which you've already seen. I'm not going to show that real quickly for you. Again, nice flat material here. I will move over to this is a 16 fiber SWR 200 micron pitch. And you'll notice when I have these conversations with you, I'm spelling out not only the coating diameter, I'm spelling out the pitch width that we're dealing with this fiber combination. So if I spread this apart, you're able to see the numbers of fibers associated with this. Another sample I'll be able to show you. This is a SWR 200 micron coated, but notice the fiber holder that I have in here. This is the F870 12 PC. The PC stands for pitch conversion. And if I drill down and look at this very closely for you, even though it's 200 micron, notice that the spacing coming out of the fiber holder is, there are small gaps between these fibers. This is critical. So when we go to splice this with 200 micron V grooves, you have to make sure that this ribbon array is holding this particular position. This helps you greatly through the cleaving. If you're complaining about your cleaver, this is a big part of it. If you're complaining about your machine not working, getting high fiber offsets, this plays a big factor into it. So these fiber holders, if I can show you one with the open position in the fiber holder ridge, if you look at that fiber holder, again, this could be cleaned a little bit, but you can see that this actually has simulated peaks and valleys as you would see within a V groove. These are a glass resin molded fiber holder. The V grooves themselves within the splicer are a ceramic ground V groove with a high degree of precision. I'm going to take this one out, look at a couple more samples, and we'll move on. I actually like this sample quite a bit. This is a 200 micron coated fiber. And let me drill down. Hopefully I can get this focused for you. Aha. So this is a 200 micron loose tube fiber that has been run through the ribbonizing tool and placed into the F870-12 PC fiber holder. Look how nicely these fibers are orientated, and the more precision you have of guiding that fiber to the back of the V groove of the fusion splicer head, the more success you will have as far as your splicing process. The last one I'll show you is a 12 fiber 200 micron spider web ribbon in pitch conversion. Actually, I apologize, it is not. I've got a lot of sample here. This is a 200 micron F870-12-200 micron fiber holder. Let me pull this back a little bit. So this is designed for 200 micron spider web ribbon, 200 micron coated fiber. As I said earlier, if you're doing 200 micron to 200 micron, left and right side, the best possible scenario as far as accessories would be the 200 micron pitch B groove versus the 250. If you can avoid pitch conversion, I highly recommend that you go down that path. The main reason for is ease of use, just simply a better decision to go down that, and you'll get higher consistency, higher quality, faster splicing times. Okay, we'll move back over and actually talk a little bit about the hot jacket stripper, and I'm going to strip some of these fibers if we can get an overhead view. And what I'm going to do is take this first sample, the match clad single mode fiber, and I'm going to turn the hot jacket stripper on. The heating profile, if you have a mode set up in your Fusion Splicer, the splicer will communicate to the hot jacket stripper and set up the correct profile. In this particular case, I believe I have the mode in the Fusion Splicer set up in SM Auto. Since I'm doing a traditional matrix material, this Corning ribbon, a couple of things about this. This is kind of old school, very easy to operate. And I'll make a quick strip and prep for you and kind of describe. And I always use this during my initial training with my customers because I want to spell out a couple of things with this. The first thing is my strip length. I have no concerns about going a little bit long with the fiber holders you see here. Drill down, look at the closer view. Just so you know, Mega's tapping me on my shoulder and told me to get in view so we can actually see what I'm talking about. Now, this length, I'm not too concerned about. I can be a little bit short, a little bit long, because the beauty of this fixed matrix material is I go to strip this, I will hold it under pressure. The thing that you have to remember with a hot jacket stripper is that there are some friction points within the hot jacket stripper. Of course, you've got the ribbon being held by the fiber holder cover itself with a rubber boot on top of the lid. You have this small foot that will come down and pinch and press the ribbon into the fiber holder in the hot jacket stripper itself. As I go to hold this, the general rule of thumb is that I want to hold this with firm pressure. When it turns from red to green, open it up. And actually, I had something happen here, and I noticed it immediately. I had a little bit of slippage occur. If you can drill down, let me show this to the team here. If you look at this, you can see this coating moving out of the fiber holder. I'm going to clean it because I don't want to contaminate the pad of my cleaver. But the reason I want to pull this out is that I move this to the CT50 cleaver. You will actually see a negative here. As a result of that fiber holder slightly slipping, you will notice here the coating has come up on top of the pad, the elastomer pad of the CT50 cleaver. Let me talk about cleavers 1 second. I want to go over and show all about cleaver little drawing. This is a theory of cleaving paper we presented probably 15 years ago. But a cleaver is all about balance. Left side equals right side. So when you clean this fiber and you get that cladding, which the primary coating has been removed, your 125 micron cladding is exposed, you want to get that fiber squeaky clean. Anything that cladding comes in contact from that point forward should also be squeaky clean. I actually mentioned the splicer earlier, the V-grooves, the V-groove chip clamps. There's only 2 pieces inside a splicer that has contamination issues and it causes actual offset problem. But with the cleaver, I can point those out real quickly. It's the left pad, upper, lower, the right pad, upper, lower, the blade itself, and this anvil. You want all this stuff to be in balance, even pressure, even tension. So as we go to cleave this fiber, I love this image because this is showing the blade in scale to the fiber. A lot of folks thinks either the cleaver blade will cut the fiber completely in half or it will barely touch it. In fact, if you look at the relationship here, the fiber, this is your fiber in the very top corner here, this little small speck that you see on your screen. If I take this and run the blade under the bottom, what actually happens is the blade itself will pass underneath the fiber, and it will produce a scribe on the bottom of that fiber, producing your depth of scribe, as we call it. I will point out here, new blade, set low to reduce blade wear. A worn blade, you set at a higher height, and it's required to produce the adequate depth of scribe in order to produce a quality cleave. With fusion splicing, it's pretty interesting because if you're doing a 12 fiber mass fusion splice, it only takes 42 splices to produce approximately 1,000 cleaves. If you're doing a 16 fiber mass splice, 32 splices will produce 1,000 cleaves. About 1,000 cleaves is kind of the average for blade wear, where we have to make an adjustment to the blade going from position number 1 to position number 2 to position number 3, so on. So that being said, pay attention to the cleaver. It's I always tell people it's 1/10 the cost of a fusion splicer, but it's half your splicing process, and that is the element that you really have to pay attention to moving forward. Now, let me move back to my demonstration right quick. So I'm going to take this fiber and I'm just going to slide it back for the sake of saving some time. And it's okay to do that in the field. It's not a problem to do that. What I want to make sure is that coating doesn't slip and come on the top of that cleaver. That's one of the key points that you want to pay attention to. Now, I'm going to move over to my microscope view. I'm going to clean this right quick and go over to my microscope view. Be patient with me, guys. What I'm doing is cleaning the fiber and trying to get the fibers to align. And now I don't know if I can peel out the definition for it. I'm going to try.
Sure. That's good.
Now, I always tell folks this, when I'm prepping the fiber, before I ever get to the cleaver, I want these fibers to simulate teeth coming out of a straight tooth comb. You want all fibers to be parallel. You don't want them touching. If I go back and look on down the line here, you can see a couple of elements here, what I would call separations, entanglements. And this can be a result of many, many things. I always, when I'm doing a customer training, when I get to this point and the customer goes, can you change the view back to the accessory?
Sure.
Yep. As I tell the customers, as they go to load this fiber in, you can see these little bit of entanglements and a little bit of, again, separation entanglements. Look how clean that looks, nice and shiny. When customers are doing their own what I call repetitive work, and I'm overviewing everything as an instructor, the point of them going to load this fiber into the cleaver, I asked them to hand me that fiber holder. If you do not see this, I would really be cautious about pushing it through your cleaver. if you got an entanglement, if you got a separation, here's where the actions of the technician becomes a problem for the cleaver. And again, this is across the industry. I'm talking about Fujikura CT50 in this particular case, but this would be any cleaver that I ever known produced that is a 3-step cleaver, strip, clean, cleave. We all would have the same type of situation happen at this point. So be cautious at this point. Now, I'm going to move over and show you a spider web ribbon. And I'm going to have to find my glasses because my cohort in crime here found my glasses for me so I can actually see. Now, this is spider web ribbon. This gets into an issue that I like to describe with rollable ribbon, loose tube ribbon, these types of materials. Shorter strip lengths actually improve your ability to be successful. The first thing you've got to ensure is that the fibers are setting in the proper V grooves. As I close this clamp down, if I go and look at my distance markings on my hot jacket stripper, this is my personal preference. You can go longer if you like. I like to use the, you see the, give me that paintbrush. Thank you. I like to use this illustration on a paintbrush. If I tell people in order to clean their cleaver, they should go to the store and get a 3-inch paintbrush and cut about 1/3 of the bristles off the paintbrush. But this is a great illustration of the bristles on a brush. If they're very long, what happens is the fibers, the bristles on the brush will have a tendency to deviate from where they're on their base plate or the backing. The same thing goes with the fibers that you have in a ribbon array. The shorter they are, the more they will stay rigid, and they will have a tendency not to separate and come together as you go through the stripping process. I'm going to strip this fiber. You'll also notice here, I will use a little technique. Can you do a pan view? As I mentioned earlier, I'm going to change my heating profile, and I'm going to go from a setting of 2 and move it up to 4. Well, hold on, let me do it on my splicer. Can you show the view on the splicer? Thank you. And again, this is just a mode inside the splicer. Change this to manual mode, turn that off, reset, and I can come back over here to my hot jacket stripper, and I can set up my temperature profile and move that to 4. Now, if I were doing spider web ribbon, I would just simply tell the splicer to switch it to 4, and it would automatically change it over to 4. In this particular case, I will strip this ribbon. Now, I will also use a little technique where I'll come back. I don't know if you can see my hand, but I will grasp the ribbon itself with my pinky finger and my ring finger to provide a little bit more tension as I go to strip this fiber. Again, the point I'm trying to make here is I'm avoiding that coating coming out of the fiber holder and getting up onto my elastomer pad and my cleaver. You'll also know, if you can drill down. Thank you, Mega. You'll notice here the coating that has backed up the side of it. This is if I do loose tube fiber. This is if I do rollable ribbon. If you're doing traditional ribbon, it will come out as a complete matrix, and you can discard that very easily. By the way, this is a nice tool for this purpose, to clean the debris out of your hot jacket stripper. Now, I'm going to prep this fiber using a cleaning wipe and an alcohol. to clean this ribbon. Now, you can drill down for me, Mega. This is an important step to consider. And again, it's called cleaning the fiber, and I also call this fiber management or training the fiber. Okay. You'll notice I grab it and I got two crisp edges, bottom and top of my wipe. I've got a clean Chem wipe. You'll be surprised how many vans I get in, and I've seen technicians use a wipe all day long. Cheapest thing in fiber optic, so this is something you want to not be shy about replacing. Now this ribbon, if I have any issues with it, I will use my cleaning mechanism to pull the fibers in position. So if I notice that the fiber number 11 and 12 were protruding downward, I would have no problem with taking this wipe and pulling that fiber at a high angle to get this fiber to come into the right position. And it all goes back to what I'm trying to achieve with my cleaver. As we get this produced, I should be able to take it to my cleaver, drop it in position. Now, if you could drill down a little bit more for me, Becca. I'm trying to get the right angle for you. Okay. So if you see this angle, notice here that I've got a little bit of separation between fibers 3 and 4. Little nervous about this. If you get a poor quality cleave, it's really not the calibration of the cleaver is causing the problem. It's where this cleaver with the fibers in here are slightly imbalanced. I would not go and press this forward. Honestly, I would probably make a little bit of adjustment for it. And you'll notice here also that the fibers themselves are barely over the apex of the fiber collection system. So we're going to make a quick splice. I'm going to take this out. I'm going to put my 12 fiber ribbon array in on my fiber. You'll notice here how clean and balanced it is. Cleave the fiber. Now, if you can move over to the head position of the splicer. Can you drill down?
Sure.
Now I'm going to take this fiber and I'm going to move it over to the head of the splicer. If I've done my job correctly with the prep work, when I go to drop this in, you will notice that the fibers will find their appropriate V groove very, very quickly. And I'm going to move over and I'm going to attempt to cleave the spider web ribbon that I've been working on. And again, make a quick adjustment here. I don't like that, so I'm going to back it out. I haven't cleaved it yet, so I'm still good. Looks a little better. I'm going to cleave it. Again, if I look at my reflections, I would say that's marginal. Move it over to the head of the machine. Now, you'll notice here, I'm having to play with it. See, the fiber's not setting down. Very much typical. I'm going to switch it out right quick. Don't like it. Let's try it again. Come over to the hot jacket stripper. Change the pan over. So if anybody's picked up on this, I actually moved because we're hurrying for time, I actually moved to a traditional ribbon. Notice how quickly that fell in position. I'm going to hit reset on my splicer. You can go over to the splicer screen. Now you should see a nice warm glow. I would be interested to see any hot spots. Here I've got a error. Notice here the error is 5.1 degrees. This is real-time splicing for you guys. This happens in the field all the time. This one would be a situation where I would re-prep that left side, strip, clean, cleave, and prep that left fiber again. Even though it's 5.1 degrees, the number here is 5 degrees. Actual offsets, one thing that I would be real concerned about here looks very good. This number 1 is 3.9 degrees. That can be attributed to a slight misalignment of the fiber holder in relationship to the V groove. It could be contamination in the V groove. It could be contamination on the surface of the cladding. Here, cleave angles, everything looks good, but that 5.1, by the way, the magic number here, excuse me, is 5 degrees. I'm going to press set. I'm going to override it. And you will notice here a nice warm glow. There's no really large projection of bright spots, which would indicate a bubble in the splice. And notice here, even though I had that cleave angle of 5 degrees, my estimate on number 9 was at 0 degrees, which is not optimal. Certainly, it's one of those type of things you have to be careful with in the field. I do not like overriding our lawns in real-time circumstances. Can we look at the overhead? We're talking a little bit about debris, and this is a major cause of issues with fusion splicing. If you're getting a bubble in your splice, it is more than likely an issue where you've got contamination. You can actually, if you attempt to clean the fiber after it's cleaved, you will roll that debris on the end of the fiber. It will get trapped in an air pocket as that arc happens. Again, this arc produces a plasma field. You heat the glass up to roughly 1600 degrees centigrade. And if that particle gets trapped between those two pieces of glass that are fused together, it will outgas and a bubble will be created as a result with it. Very common in the industry and something we see all the time. That's pretty much it for my presentation. We're going to go to the questions, and Mega's going to ask them, and we'll move forward.
Okay, awesome. This was informative, Greg. Thank you. So we do have few questions. One of them is, how do I change a 90R V groove? So how do they change the 12 fiber to 12 fiber 200? That is the 12-200, also with 16 and 16-200s. So basically, to start off, our 90R supports all the configurations I just mentioned: the 16 fiber 200, 16 fiber, 12 fiber, and 12 fiber 200. So it is a simple change, and Craig is going to show that right now. There you go.
To exchange the V grooves, you just simply come in and remove these 1.5 millimeter cap screws. You've got one on the bottom right and then one on the top left. It's simply a point of removing, lifting, and replacing. Of course, when you put in new V grooves, you will want to stabilize your electrodes. And what stabilization means is, if you look at these electrodes, it's probably going to be a little bit hard to see them, but they are kind of white on the tip. This is where glass has been vaporized and the silica oxide on the tip of that electrode. Happens very quickly, but if you replace the V groove in the electrodes, you want to stabilize these electrode pins to get that silica oxide in place and then you would do an arc calibration from that point to get ready for the next splice you're trying to make.
Okay, thank you. We have another question here asking us, how do you get 90R to display estimated loss after splice is complete?
Simple. What you would want to do, if I show the monitor, press menu. If you go into, I think it's other settings, machine settings, and I'm wrong. I'll have to back out. My apologies. You caught me a little off guard with this one.
Until then, let me go back to the question we have, which asks you, can you discuss the importance of our calibration and why it's important? Our calibration is very important because you want the machine to work as intended, and when you're using a splicer, the environmental factor is affecting your splicer. Let's say you're in a hot, humid regions. For every 10 or 20 splices, you would be start to see the wear off, and you can get some limits in there. So it is better every day. You have to do an R calibration, and I would say every time you change the fiber type, it's a good practice to do the R calibration. And you can find that in the calibration menu. You have a lot of other setups in there where you can go through R calibration and electrodes and other things there. Anything to add, Craig?
Mega's correct. The main thing with arc calibration is you have to do this almost on a daily basis due to the barometric pressure changes. When you have a hot, like a high pressure system roll into town, it will actually compress the oxygen molecules. You will have more oxygen present. As a result, your arc will burn hotter. So it's why we recommend daily arc calibrations.
Okay, awesome, thank you. And will 90 series splicer help with the polarization maintaining fibers?
No, it does not. We do have a PM, which we call polarization maintaining fusion splicer, that has not only X, Y, ZL, ZR, but it also has theta motion, theta left, theta right. That is a rotational axis motor that will allow you to rotate and align the stress rods within a polarization maintaining splicer. We do have that available, but not on a field
90
style
series
machine,
version,
90
basically.
series splicer, yes.
Please reach out to AFL. One of our associates will be happy to help you with what we have in the factory specialty side, and you can explore that more in our AFL website. It is called a specialty fusion splicer. Is there any necessary setting when splicing a 200 to 50 micron fiber? So to start off, I would ask you, a 200 250, do you mean a 200 pitch 250 coating diameter, or a 200 200 or a 250 250? So that is a very important nomenclature you have to keep adding up whenever you introduce a fiber.
That's correct, Mega. When we first started in the industry, we were more concerned, is it a single mode fiber, is a multi-mode fiber? We really were talking about the glass composition, what type of dopants were present in the optical fiber. Now we're getting into some mechanical structures of the assembly itself. What's the coating diameter? Is it 200? Is it 250? What is the rollable ribbon structure? What is the fixed matrix structure? These things are critical to understand so that we provide you with the correct fiber holder V grooves in order to give you what I call good, better, best, provide the best operational situation that you can have in the field environment.
Okay, that is awesome. Thank you. So we did get that is a 200 core and a 250 core diameter. So For that, I would say please use a pitch conversion fiber holder. So basically you can convert the 200 to 250 and you can use the same V groove, the 250 V groove, and complete the splicing. So that will not be a problem. And also we have another question asking us, will a 70R splicer work for 16 fiber, or is it just 90R? So both our 90R, 70R, and the older ones support the 16 fiber 16 fiber splicing. Please reach out to us and we can give you more information on how we can basically do that.
The 90R has V grooves available for 8 fiber, 250, 12 fiber, 200, 250, 16 fiber, 200, 250. If you have an old legacy 70R, it is not retrofittable with V grooves. The newer 90 series and above would have that capability.
Okay, awesome, thank you. And as you have seen that there was a problem with the spiderweb ribbon, there was some entanglement between the fibers. So do you have any tips to our viewers how to overcome the problems with this spiderweb ribbon?
Honestly, that's kind of one of the things I wanted to elaborate about AFL's capabilities and what we bring to the table. Not only are you getting a state-of-the-art system with a company that's heavily engineered and designed Fusion Splicer for well over 35 years, what we have done is we've got a tremendous service department and a tremendous application engineering group here that includes many, many members. And we have invested heavily to give you that type of support as you go down these paths of splicing whatever would come across you. That's when you want to reach out to us and let us assist you. We try to cover a lot in an hour time frame. Typically, a mass fusion training session would last 2.5 hours, and this would be your just basic operational training. Then you get into the level of detail that we're having discussions about now.
We have plenty more questions, but as we don't have much time to go over everything, we will return back with the answers individually. So I would end this presentation with saying thanks to everyone who has attended it. Please visit the AFL Global website to find more of our splicing products, accessories, and all our new solutions for 16 fiber and different things we are launching soon. So thank you everyone for your time. I hope you have a good day.
Let me add one other thing. We're here to help, and happy holidays, everyone. Have a great
happy holidays.
Great holiday. Bye-bye.
Thank you.
Thanks, Craig. Thanks, Mega, for the demos. Thanks, everyone, for joining in and the questions today. So what we're going to do, we're going to send a survey out after, and we appreciate all of your comments on this and future webinars. And a link will also be sent out tomorrow to the recording for viewing. So this concludes the webinar today. We hope you all have a good evening. Thank you very much.